Much like describing the mean of a population, we may also be interested in studying the proportion of a population that falls into one of two categories. Naturally, the notion of two categories is the same as our previous discussion of the binomial distribution. For example, when we collect a sample of output parts resulting from a manufacturing process, each observation in that sample either lies within specification or falls outside of specifications. We can count the number of observations in the sample that fail to meet specifications, ultimately calculating a point estimate of the proportion of the sample that falls outside of specs, y divided by n. We can then use this point estimate to draw inferences about the population proportion using a confidence interval. Other examples include the proportion of structurally deficient bridges in the population of bridges, as a bridge falls into either structurally sound or structurally deficient categories, or the population proportion of correctly identified objects found from a radar image, as images are either correctly or incorrectly identified. The mechanics of the confidence interval for a population proportion are similar to that of the interval for a population mean. We find a point estimate, then add to it and subtract from it a margin of error. And, like before, this margin of error is a function of variability, sample size, and confidence. We collect a sample of size n from the population, and we determine the number of observations, y, that fall into the category for which we want to find the proportion. Naturally, y observations fall into the category we're interested in, and n minus y fall into the other category. The notation for the sample proportion is p hat equals y divided by n. Back to the manufacturing example, say we collect a sample of 135 parts and find that 12 fail to meet design specifications. The sample proportion of parts not meeting specifications is p hat equals 12 divided by 135, or 0.089. We could use 0.089 as an estimator for the population proportion of parts produced in our manufacturing process that do not meet specifications, or more appropriately, we could calculate a confidence interval. The 1 minus alpha times 100% confidence interval for population proportion has the following form: p hat plus and minus z alpha over 2 times the square root of p hat times 1 minus p hat over n. The measure of standard deviation, the square root of p hat times 1 minus p hat over n, comes from the binomial distribution. And we use a z value to represent confidence. In our example, the 95% confidence interval for the population proportion of parts not meeting specifications is 0.089 plus and minus 1.96 times the square root of 0.089 times 1 minus 0.089 divided by 135. And that is 0.041 and 0.137. That is, the proportion of parts not meeting specifications in the population of parts produced in our manufacturing process lies between 0.041 and 0.137 with 95% confidence. For some, interpreting this as a percentage may be helpful. Between 4.1% and 13.7% of parts produced in the manufacturing process lie outside the specification with 95% confidence. A couple of notes to be aware of. From a notation perspective, some textbooks use q hat to represent 1 minus p hat, or the proportion of the other category for which we didn't produce a confidence interval. As such, the confidence interval would be written as p hat plus and minus z alpha over 2 times the square root of p hat times q hat divided by n. There is also an assumption that the confidence interval won't contain 0 or 1. That is, that the lower bound of the confidence interval won't be negative, or that the upper bound won't be greater than 1. In either of these cases, we'd be producing values that don't describe proportions, which must be strictly between and inclusive of 0 and 1. We primarily try to ensure that the interval won't contain 0 or 1 by increasing the sample size n, thereby ensuring that the margin of error is sufficiently small. A common rule of thumb is to check that both n times p hat is greater than or equal to 4, and n times 1 minus p hat is greater than or equal to 4.